Hello everyone. Today I will be presenting about binary search trees, also known as BST. This topic focuses on three main operations: insertion, deletion, and traversal, which are fundamental to understanding how data can be stored and accessed efficiently in computer science. A binary search tree is a special kind of binary tree that follows a strict ordering rule. For every node, the values in the left subtree are smaller than the right node's key, and the value in the right subtree are greater. This structure allows quick sharing, insertion, and deletion operations, usually in logarithmic time. For example, if the root node has a value of 50, then 30 would go its left since it's smaller, and 70 would go its right since it's greater. The rule must hold true throughout the tree. BST are very useful because they support dynamic operations like searching, insertion, and deletion data efficiently with an average time complexity of O. It means log n. Another major benefits is that BST maintain elements in this sorted array automatically, making data retrieval faster and easier. They are widely used in areas such as database indexing, sorting, algorithms, and associative arrays. When inserting a new value in a BST, the process begins at the root node. We compare the new key with the current node's key. If it's smaller, we move left. If it's larger, we move right. We keep doing this until we find an empty spot and then we insert the new value as a left node. This ensures that the BST property is maintained throughout. Take an example of inserting the sequence 50, 30, 70, 20, 40, 60, and 80. Each new key finds its correct position according to the BST rule. The result is a well-structured and mostly balanced tree. Insertion efficiency depends on the tree's height, XO, for a balanced tree but can degrade to O. If the tree becomes skewed like a linked list, both recursive and the iterative insertion methods exist. Though recursion often provides a simpler code, deletion is slightly more complex because it must preserve the BST property. There are three cases. First, if the node is left with no children, we can simply remove it. Second, if it has no child, we replace the node with its child. And third, if it has two children, we replace it with its Inorder successor, the smallest node in its right subtree, and then remove the successor from its original position. This ensures that the tree remains valid and properly ordered. In the case where a node has two children, says where we are deleting the node with value 30, we find its Inorder successor, which could be 40. We replace 30 with 40 and then delete the original node 40 from its position in the right subtree. Replace keeps the BST property intact and avoids complicated pointer rearrangements. Traversal means visiting every node in the tree once. There are three main traversal methods. Inorder traversal methods that follows left, root, right order and give the elements in sorted order. Preorder traversal goes root, left, right and is useful when copying or reconstructing a tree. Postorder traversal follows left, right root and is used when deleting or freeing memory from the tree since it processes children before their parents. Let's look at an example using the same BST when we perform and in order traversal on nodes 50, 30, 70, 20, 40, 60 and 80, the output will be 20, 30, 40, 50, 60, 70, 80. This confirms that the BST correctly maintains elements in sorted array, which is one of the most powerful properties. To summarize, binary search trees provide an efficient way to store and manage ordered data. They support fast operations with an average time of O, but maintaining the BST property is essential during insertion and deletion. Traversals like Inorder, preorder, and postorder allow structured data access. Finally, for even better performance, balanced trees such as AVL or red-black trees are used to prevent worst case scenarios. Thank you for listening.